How does a tire filled with ordinary air become a potential bomb at 38,000 feet? And why, at the exact moment a 560-ton aircraft slams back onto the runway at 290 kilometers per hour, does the gas inside that tire determine whether everyone on board walks away? And why does every airline on Earth, from a budget carrier running aging 737s to the engineers behind the Airbus A380, all agree on one specific molecule that regular air simply cannot match? To understand what's at stake, you need to feel the numbers first. A fully loaded Boeing 777-300ER touches down with a maximum landing weight of 251,000 kilograms. That's the equivalent of stacking 167 adult male African elephants on a 6-tire main landing gear. Each of those tires is inflated to roughly 200 psi. That's 14 times the pressure in the tires of the car sitting in your driveway right now. The tire on your daily commute handles potholes at 35 psi. These tires absorb the kinetic energy of a controlled fall from the sky in under 2 seconds, repeatedly, sometimes 14 times a day. So how exactly does the gas inside that tire make or break that moment? The answer starts in the early days of commercial aviation, when the answer to the question, "What do we put in airplane tires?" was exactly what you'd expect from an industry still figuring out how not to kill people. Compressed air, pumped from a standard ground compressor. And for a while, it worked. Mostly, propeller-driven aircraft of the 1930s and 1940s were lighter, slower, and landing speeds rarely exceeded 130 kilometers per hour. The rubber held, the air held, and nobody asked too many questions. But then something changed. Aircraft got heavier by orders of magnitude. Jet engines meant cruising altitudes above 10,000 meters. Landing speeds climbed past 250 kilometers per hour, and engineers started noticing a problem that regular air had been quietly hiding from them all along. When you compress regular air into a tire, you are not just compressing one gas. You are compressing a cocktail, roughly 78% nitrogen, 21% oxygen, and trace amounts of argon, CO2, and water vapor in various forms. At ground level, on a cool morning, that cocktail behaves itself. But at 38,000 feet, the temperature outside the aircraft's skin drops to negative 56 degrees Celsius. And on landing, when the wheel spins up from 0 to 290 kilometers per hour in the first fraction of a second after contact, friction heats the tire from the outside, while the compressed gas inside is still at altitude temperature. The tire doesn't just warm up. In extreme cases, brake heat builds to over 1,000 degrees Celsius during rejected takeoff scenarios. And here is where regular air reveals its fatal flaw. Oxygen burns. This is not a complicated concept, but its implications at aircraft tire pressures are catastrophic. When a tire suffers a structural failure or a brake overheats to the point of ignition, the 21% oxygen inside a standard air-filled tire doesn't just allow combustion, it actively feeds it. Rubber at high pressure, inside a wheel well packed with hydraulic lines, fuel system components, and structural aluminum, does not need much encouragement to turn a brake fire into something significantly worse. Aviation engineers looked at this risk and made a decision that sounds almost absurdly simple. Remove the oxygen entirely. Nitrogen is what remains. Pure, dry, inert nitrogen. The same gas that makes up more than 3/4 of the air you're already breathing. It is pumped into aircraft tires at a purity level above 95% and often above 98% on commercial jets. And this is where most people assume they already understand the story. They think nitrogen is used purely to prevent fire. They are half right and half wrong. And the half they are wrong about is the part that is actually more interesting. Here is the myth. Nitrogen is heavier than air, so it leaks more slowly. You may have heard this in the context of car tires, where it is mostly a marketing claim with only marginal real-world benefit. In aircraft tires, the leakage argument matters, but not because of molecular weight. Nitrogen molecules are not dramatically larger than oxygen molecules. The real reason nitrogen holds pressure more consistently inside an aircraft tire has nothing to do with the molecule's mass, and everything to do with moisture. Regular compressed air carries water vapor. If you've ever watched a pneumatic tool release a burst of moisture-laced air on a cold day, You've seen water vapor condensing out of compressed air in real time. Now take that same phenomenon and scale it to aircraft operating conditions. At altitude, temperatures inside an unpressurized wheel well can drop to -40 degrees Celsius. The water vapor inside a regular air-filled tire does not stay as vapor. It condenses into liquid water, and then, in severe cases, it freezes. Liquid water pooling inside a tire adds unpredictable mass imbalance. Frozen water at the base of a tire, with the wheel at rest during cruise, can create a flat spot that the tire never fully recovers from. And more critically, as the tire heats rapidly on landing, that trapped moisture turns to steam, creating a micro-pressure spike inside an already highly stressed structure. Nitrogen, when supplied at aviation-grade purity, contains almost no moisture. The dew point of aviation nitrogen is specified to reach as low as -65 degrees Celsius, meaning there is effectively no water vapor present to condense, freeze, or flash into steam. If you were to crack open a commercial aircraft tire valve and measure the humidity inside, it would read close to zero. The tire's internal environment is, in the most literal sense, engineered to be indifferent to temperature extremes. Now consider the pressure consistency this enables. Tire pressure on a commercial aircraft is checked before almost every flight. A tire inflated with regular air and subjected to the temperature swings of a trans-Pacific route. From a humid 35-degree day in Singapore to the thermal shock of cruise altitude, and back to a runway baking at 40 degrees in Dubai, will show pressure variations of 8 to 12 psi throughout that journey, just from moisture behavior alone, before accounting for any physical leakage. A nitrogen-filled tire running the same route in testing shows a variation of under 2 psi. That 10 psi difference is not trivial. Manufacturers publish tire pressure limits with tolerances measured in single-digit psi. An underinflated tire at landing doesn't just wear faster, it flexes excessively under load, builds heat in the sidewall, and in catastrophic cases, can separate. There is one more layer of hidden genius in this system that most people never consider. Aircraft tires are not simply replaced when they go flat. They are retreaded. The carcass of a commercial aircraft tire can be retreaded up to 7 times, with the structural belts and casing carefully inspected and recertified between each use. The nitrogen atmosphere inside the tire between uses acts as a preservation environment for the rubber compounds and bonding agents in the carcass. Regular air, with its oxygen and humidity, accelerates oxidative degradation of rubber over time. A tire stored fully inflated with nitrogen for months between inspection cycles arrives at its next retread with its internal structure in significantly better condition than the same tire stored with regular air. The airline isn't just filling the tire with nitrogen for the flight. It is preserving a precision-engineered component worth thousands of dollars per unit across its entire service life. Every single time a commercial aircraft touches down, hundreds of thousands of times per day across the global fleet, that moment of violence between rubber and asphalt is managed by a century of material science, a decision made decades ago about a single molecule, and a level of engineering intention that extends all the way down to the precise humidity specification of the gas inside a tire that most passengers will never once think about. The invisible choices are almost always the ones keeping you alive.